Hello fellow mathematicians. In the last video, we learned about the mathematics underlying Lagrangian mechanics, and we proved why the principle of least action truly describes real-world processes. So in the second episode of Lagrangian mechanics, we are going to learn about the double pendulum, and we'll use the power of Lagrangian mechanics to describe this complex physical system. So the double pendulum begins with a seemingly simple setup. So we have a ceiling. So we have a rod of length L1 attached to a bob of mass M1 attached to a particle. Then we have another rod of length L2 attached to another particle or bob of mass M2. So this is a double pendulum. And some important assumptions must hold here. First of all, there shouldn't be any friction or air resistance or things like that. Also, the rods should be rigid, so they don't bend or stretch or anything like that. And the rods should be massless. So with those simple physical assumptions, we can proceed to figuring out how to describe this. And this is atrociously difficult in Newtonian mechanics because of the quantities that Newtonian mechanics requires us to find. But with Lagrangian mechanics, writing all the equations down is much simpler. So what we're really trying to do here is find theta 1 as a function of time and theta 2 as a function of time, where theta 1 is the angle of the first rod with the vertical, and theta 2 is the angle that the second rod makes with the vertical. And so if we can find theta 1 as a function of time and theta 2 as a function of time, or at least create equations of motion that describe these two variables, then we have successfully described the entire system. And so how do we begin here? Well, we want to first find what the Lagrangian is. And of course, that's 1/2 mass times velocity squared. So here, we're going to have to split it up. We're going to have to add the total kinetic energy and subtract the total potential energy. So first we're going to have 1/2 m1 times v1 squared, that's for the first bob, plus 1/2 m2 v2 squared for the second bob. And then we will subtract off the potential energy. Here the potential energy is going to be m1 g y1 and m2 g y2, where y1 is the height of the first bob and y2 is the height of the second bob. So in order to find these velocities and these heights, we have to figure out the x and y coordinates of both bobs. So x1 and y1 are the coordinates of the first bob, and similarly for x2 and y2. And here we're creating a coordinate system where this is the origin. So first let's look at x1. Some simple trigonometry tells us that that's equal to L1 times sine theta 1. Then for y1, similarly, that's going to be equal to negative L1 times cosine theta 1. And that is negative, of course, because again, the origin is here, so all the bobs are currently below the origin. And then for x2, we add L1 sine theta 1 to L2 sine theta 2. And that is our x-coordinate. And then the y-coordinate, similarly, is going to be negative L1 cosine theta 1 minus L2 cosine theta 2. Okay, so that takes care of these y-coordinates. However, to find the velocities, we still need to do a bit more work. So this is the overall velocity, not the velocity in the x direction or in the y direction. So if we have the velocity in the x, the velocity in the y, this is the velocity that we're looking for. And so in order to find it, of course, we use the Pythagorean theorem. V squared equals Vx squared plus Vy squared. So here, of course, the velocities in the x are going to be x1 dot and x2 dot, and the velocities in the y are going to be y1 dot and y2 dot. And so if we want to find v1, then we just plug into this equation. So we have v1 squared equals x1 dot squared plus y1 dot squared, and similarly for v2. So we need to find the derivatives of all of these coordinates with respect to time so that we can plug them into here. So we begin with x1 dot. So L1 is obviously a constant. And then here this is tricky because remember that theta 1 is a function of time. So we have a function of a function and we have to use the chain rule. So first we take the derivative of the outside with respect to the inside. The derivative of sine is cosine. So we have cosine theta 1 multiplied by the derivative of the inside with respect to time. So that's going to be theta 1 dot. Similarly, y1 dot. Here the derivative of negative cosine is positive sine. So we're going to have L1 sine of theta 1 times chain rule theta 1 dot. And then for x2, we proceed in a similar way. We have L1 cosine theta 1 times theta 1 dot plus L2 cosine theta 2 times theta 2 dot. And then for y2 dot, we're going to have L1 sine theta 1 dot plus L2 sine theta 2 dot. Okay, so now we can finally plug all of these values into our Lagrangian. So first we find v1 squared. That's going to be equal to x1 dot squared, L1 squared cosine squared theta 1 times theta 1 dot squared plus y1 dot squared. So that's going to be L1 squared sine squared theta 1 times theta 1 dot squared. So here we can simplify this a bit. We can factor out the L1 squared times theta 1 dot squared, and then inside we're just going to have cosine squared theta 1 plus sine squared theta 1. And of course, according to the Pythagorean identity, that's just equal to 1. So we're left with what we factored out, which is L1 squared theta 1 dot squared. Very simple. However, for v2 squared, it's going to be a bit more tricky, but we'll still have some nice simplifications. So first we have x2 dot squared. So we'll have to square this binomial. So we'll have L1 squared cosine squared theta 1 dot squared plus 2 times L1 times L2 times cosine theta 1 cosine theta 2 times theta 1 dot times theta 2 dot. And then we have the last term. We have L2 squared cosine squared theta 2 dot squared. Then we do a similar thing for y2 dot. So we're going to have L1 squared sine squared theta 1 dot squared plus 2 times L1 L2 sine theta 1 sine theta 2 theta 1 dot theta 2 dot. Then finally we're going to have L2 squared sine squared theta 2 dot squared. Okay, so we can do a lot of simplification here. So first, let's look at these two terms. So here we can factor out an L1 squared times theta 1 dot squared. And similarly to before, inside the parentheses, we're just going to have cosine squared theta 1 plus sine squared theta 1, which is just equal to 1. So then we're just going to be left with L1 squared theta 1 dot squared. Then we can do a similar thing for these two terms. We can factor out L2 squared theta 2 dot squared. Inside the parentheses, we're going to have cosine squared theta 2 plus sine squared theta 2. That's just 1. So we're left with L2 squared theta 2 dot squared. Then finally, for these ones, we can also perform a nice simplification. So we can factor out 2L1 L2 theta 1 dot theta 2 dot. Then inside the parentheses, we're going to have cosine theta 1 cosine theta 2 plus sine theta 1 sine theta 2. So of course, we know that cosine alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. So we can use that identity here. So cosine theta 1 times cosine theta 2 plus sine theta 1 times sine theta 2 is just going to become cosine theta 1 minus theta 2. And then of course we have what we factored out. So we're going to have 2L1 L2 times cosine theta 1 minus theta 2 times theta 1 dot times theta 2 dot. And that deals with our V2 squared. Now let's see what our Lagrangian becomes. So we're going to have 1/2 m1 L1 squared theta 1 dot squared plus, let's distribute the 1/2 m2. So we're going to have 1/2 m2 times L1 squared theta 1 dot squared. Then we're going to have 1/2 m2 times L2 squared theta 2 dot squared. Then we are going to have, here the 1/2 is going to cancel with the 2, so we're going to just have m2 times L1 times L2 times cosine theta 1 minus theta 2 times theta 1 dot theta 2 dot. And then finally, we're going to subtract off the total potential energy. So first, we're going to have m1g L1 cosine theta 1. And here there's going to be a plus because there was a minus in the front. And then similarly, we're going to have m2 times g times L1 cosine theta 1 plus m2 times g times L2 cosine theta 2. And of course here we have plus signs because the two negatives canceled. Okay, so that's our Lagrangian, and it's finally ready to plug into the Euler-Lagrange equation. So here we have our Lagrangian, and now let's write our Euler-Lagrange equation. So that's going to be del L over del xi. Now here we have two xi. The first one is going to be theta 1, and the second one is going to be theta 2. So we're actually going to have two equations of motion. So let's begin with theta 1. So we're going to have del L over del theta 1 minus d over dt del L over del theta 1 dot equals 0. So let's put in our Lagrangian. So first we're going to have del L over del theta 1. So this term is treated as a constant because it has theta 1 dot, not theta 1. Similarly, these two terms are treated as constants. However, this term has a theta 1. So here we're differentiating with respect to theta 1, so no chain rule needed. And so all of this is just going to be a constant. And then we're going to have the derivative of cosine, which is negative sine of theta 1 minus theta 2. So then we're going to have negative m2 L1 L2 times sine of theta 1 minus theta 2 times theta 1 dot times theta 2 dot. Then similarly for this term, the derivative of cosine is negative sine. So we're going to have minus m1 g L1 sine of theta 1. And then very similar for this term, we're going to have negative m2 g L1 sine of theta 1. And then this term we treat as a constant because it makes no reference to theta 1. Okay, so that's the first term of the Euler-Lagrange equation. Now here we're going to have to do two steps. First, differentiate the Lagrangian with respect to theta 1 dot, and then differentiate that with respect to time. So let's first find del L over del theta 1 dot. So let's see, we can differentiate this with respect to theta 1 dot. So then the 2 will cancel with the 1/2. So we're just going to have m1 L1 squared theta 1 dot. Then similarly, we can differentiate this term to get M2 L1 squared theta 1 dot. And then we can drop this term because it makes no reference to theta 1 dot. Then this term differentiating with respect to theta 1 dot, we're just going to have everything else. So we're going to have M2 L1 L2 cosine theta 1 minus theta 2 times theta 2 dot. And then this term makes no reference to theta 1 dot, and these terms make no reference to it either. So now we can differentiate this with respect to time and put it into our equation. So we'll factor in the negative later. So here the only thing that depends on time is theta 1 dot. So when we differentiate that, we're just going to have M1 L1 squared theta 1 double dot. And then similarly here, we're going to have M2 L1 squared theta 1 double dot. And then here we have several variables that depend on time, so it's going to be a bit trickier. And here we have to first use the product rule. So we're going to have the derivative of this times theta 2 dot plus this times the derivative of theta 2 dot. So we're going to have some term which we're about to work out, and then we're going to add M2 L1 L2 times cosine theta 1 minus theta 2 times differentiating theta 2, we're going to have theta 2 double dot. And then here, we're going to differentiate cosine theta 1 minus theta 2 with respect to time. And so here, we're going to use the chain rule. So we take the derivative of the outside with respect to the inside. So that's going to be negative sine of theta 1 minus theta 2. And then we'll multiply that by the derivative of the inside with respect to time, which is going to be theta 1 dot minus theta 2 dot. So this is going to be a bit messy. So we're going to have M2 times L1 times L2 times sine of theta 1 minus theta 2. Of course, that's negative. Times theta 1 dot minus theta 2 dot. And we can't forget about the theta 2 dot at the end. So of course we can distribute this. So then we're going to have negative M2 L1 L2 sine theta 1 minus theta 2 theta 1 dot theta 2 dot plus, because the negatives cancel, M2 times L1 times L2 times sine of theta 1 minus theta 2 times theta 2 dot squared. So we actually have two terms because of the chain rule. So let's move this around a bit and plug these in. So now we have found all of our terms. Now we can do a few nice simplifications. First of all, let's distribute this negative. There we go. However, we have a lot of minus signs here. So let's multiply both sides of the equation by -1, since here we just have 0, and that'll tidy it up a bit. Then we can also divide both sides by L1, because one instance of L1 appears in all the terms. Then, very wonderfully, two of these terms cancel. Here we have an M2 L2 sine theta 1 minus theta 2 theta 1 dot theta 2 dot, and here we have the exact same thing, negative M2 L2 sine theta 1 minus theta 2 theta 1 dot theta 2 dot. So these terms are going to cancel. So it looks already much cleaner. And finally, we can combine some like terms here to make it even nicer. For example, both of these have a common factor of g times sine theta 1. So inside the parentheses, we'll just have m1 plus m2. So that's nice. So we can have m1 plus m2 times g sine theta 1. Then similarly here, we can have m1 plus m2 L1 theta 1 double dot. And then finally here we have two more terms, m2 L2 cosine theta 1 minus theta 2 theta 2 double dot plus m2 L2 sine theta 1 minus theta 2 theta 2 dot squared. And all of this is equal to 0. And so this is our first equation of motion for the double pendulum. So you can see that it took quite a bit of calculation because this is a complex system. But with the Newtonian approach, it would have taken even more time and effort. So now that we understand how this works, let's use basically the same process to find the second equation of motion, where we replace the theta 1 with theta 2. So finally, after all that hard work, we have our two equations of motion describing the double pendulum. And this is a system of two coupled quadratic second-order ordinary differential equations. So pretty wonderful to see. And we were able to use the power of Lagrangian mechanics to create these equations which describe the swinging of the double pendulum. Unfortunately, these equations cannot be solved analytically, as they are, of course, extremely complicated. However, they can be solved using numeric methods. So we won't do that today, but if you were to solve it, you can create some very nice simulations of the double pendulum swinging. And the double pendulum is actually a chaotic system, so it's very interesting to see it at work. So thank you so much for watching. Please apply a force vector to the like and subscribe buttons, and see you next time.